It is dawn and the sun is rising, as it has every day for the last 5 billion years. For millennia, it has been a constant golden disk shining its unchanging light onto the earth. But look through the glare, and the true face of the sun is revealed. Not constant, but constantly changing. Turbulent and violent. Its worst tantrums can wreak havoc on the earth. To understand the sun is to understand the forces that drive the universe. If we can control those forces, we can unlock the power of the stars. The power of our sun. Within the universe, there are 100 billion galaxies. Our galaxy is but one of them. In it, there are 100 billion stars. And towards the outer edge of one of the spiral arms is an almost insignificant dot. A medium-sized, not very bright, undistinguished star. Up close, it's a different story. On the planets closest to the Sun, Mercury and Venus, the heat is intense, their surface is scorched. Further out through the solar system, the Sun's rays weaken, until they are powerless against the chill of space. The outer planets are frozen. But in the middle lies the Goldilocks planet. Not too hot and not too cold. In fact, it's just right. And life has flourished in the warm glow. All life on Earth owes its existence to the sun. It powers every natural system and sustains every plant and animal. Without the sun, the planet would be a barren, lifeless ball of rock. Recognizing that power, humans have always worshipped the sun. But we have also always striven to understand it. These monuments are more than just temples. They are calendars and observatories, tools for studying the sun. And some of them are still operational. To our ancestors, its power was its reliability. Always on time, never changing. But the reality is proving to be very different.
Most people think of the sun as quite a boring, constant sort of thing, but in fact it's not at all. It's changing all the time, and if you look, you can see those changes on a matter of minutes or hours, and it's far from static and boring. It's changing, and it's got a life of its own.
Modern solar observatories magnify and filter the sun's light to get past the constant glare and give a clear view of the surface. This is the actual face of the sun. It is turbulent and boiling. Never the same from one second to the next, the surface bubbles like a giant bowl of porridge. Each bubble is 1,000 miles across. The heat and light brought to the surface raises its temperature to 6,000 degrees centigrade, enough to vaporize solid rock. And the sun is huge. You could fit the Earth inside it 1,000,000 times over. Periodically, huge explosions rip through the surface, releasing the energy of 1 billion atomic bombs in seconds. All this is on the surface. To understand the sun, we must know what is going on deep inside. That is where the power is generated. So for centuries, scientists have been devising ways to probe the heart of the sun. Some of them have been complex, and some of them very simple. And the first step is to figure out just how powerful the sun is.
It's easy to appreciate the power of the sun on a nice hot summer's day like here in the Texas Gulf Coast, and you can feel the power of the sun, your skin, sunscreen's on. But man, the sun is just, you know, the actual physics of what's going on inside the sun, the power that the sun, the energy that the sun is releasing is almost beyond comprehension.
But it is only almost beyond comprehension. And you can measure its power output with some simple apparatus.
One of the earliest experiments to try and measure the actual power of the sun was by astronomer William Herschel in the 19th century, where he had the brilliant idea of just watching a piece of ice melt to see how long it would take, and therefore from the properties of the ice work out how much sunlight was coming to the ground.
As a demonstration of the sun's power, it doesn't look that impressive. But Herschel realized that he could use the time it takes to melt one bit of ice to calculate the sun's total power output.
So here we see the ice is almost completely melted, roughly 29 minutes, almost half an hour. But Herschel was able to use this experiment and the time that it took to melt the ice to work out some basic properties of the sun.
Here's how Herschel's thinking worked. In the time it takes to melt a slab of ice on Earth, the sun is radiating heat in all directions, enough to melt a complete shell of ice around it, a diameter of 300 million kilometers. A shell half a centimeter thick and 300 million kilometers across contains a lot of ice, enough to make an ice cube bigger than the Earth. To melt that much ice in just 30 minutes would take an energy input of 1 billion watts. It's a rough but surprisingly accurate experiment. Modern satellite readings confirm the figures to within a few percent. It's an almost unimaginable amount of energy. If we could harness the sun's power output for a single second, it would satisfy the world's energy demands for the next 1,000,000 years. But first, you have to know what the sun is made of. To find that out, you need to take a very close look at sunlight.
When you take the light from the sun and pass it through a prism, spread it out into the colors, as you look through it, you notice that it isn't uniform, that there are places that are darker. Each of those dark lines is due to a specific chemical element. Each element has its own series of lines that are specific to it.
Each chemical element absorbs light at specific frequencies, removing a strip from the spectrum. As the light passes through the sun, all the elements leave their mark. So when the light arrives at the Earth, it contains the complete chemical formula of the sun.
If we take the spectrum and spread it out to fine details, and what we've done here is stack up pieces of the spectrum one on top of each other, you see all of these dark areas. The key to figuring out how much of these elements are there is the breadth and the depth of the line. How dark is the line and how broad is it?
The composition of the sun lies in this barcode. All the thin lines are caused by tiny amounts of complex elements, metals like iron and magnesium. But there are 3 very deep broad lines, and they are all caused by an enormous amount of a single element. There's some helium and traces of heavier elements, but over 90% of the sun is hydrogen. the simplest and most common element in the universe. The secrets of the sun's power must lie in this gas.